All right, now for example 4 here, we'll go ahead and solve this fourth order Cauchy-Euler differential equation. You can see it's Cauchy-Euler because, again, the exponents of the variables x's here match the order of the derivative they're attached to. So that's kind of nice. So, and in this example, is a perfect example where you do not want to memorize some type of formula. It is much better to always just remember that y equals x to the m is going to be our supposed solution to any Cauchy-Euler. And then we can see we have 4 derivatives. So everywhere that I see one of these, and in fact, I'm going to go ahead and write this out. I'm going to insert x to the m for y and m x to the m minus 1 for y prime, and so on and so forth down the line. In fact, I'm going to write this backwards so you can see it. So instead of y, I'll have x to the m. And 3x times, instead of y prime, I'll have m x to the m minus 1 plus, and instead of y triple prime, I'm going to have y double prime, I'll have m times m minus 1 x to the m minus 2. The coefficient of that was a 9x squared. And instead of y triple prime, I'll have an m minus 1, m minus 2. I didn't leave myself enough space there. Let me start over here. m minus 1, m minus 2, x to the m minus 3, and its coefficient will be 6x cubed. And then finally the y to the fourth term, and I will likely write off the edge of the page here, but there will be an m, actually I'll write it down here, m minus 1, m minus 2, m minus 3, x to the m minus, m minus 4, and its coefficient will be an x to the fourth. And you could see that with each of these terms, when you multiply the base x's together, the exponents in the end will be x to the m. So you have x to the nth times the quantity, m minus 1, m minus 2, and m minus 3, plus 9, 6, m minus 1, m minus 2. Now the plus 9, m minus 1. And finally, the plus 3, m, and the plus 1 is equal to 0. So, and by the way, that's all in bracket there. So you can see that this can be pretty large when you do these problems. We're going to distribute through and clean things up. So it takes a little bit of work at the end here. So what I'm going to do is scroll this up a little bit. I'm going to ignore the x to the nth because that does not turn this product into 0. It's all the stuff inside. So I'm going to write this as an m squared minus m times m squared minus 5m plus 6 plus 6 times m squared minus m times m minus 2 plus 9m squared minus 9m plus 3m plus 1, and this is all supposed to equal 0. You can see this just becomes a huge multiplication problem, but you would never be able to really memorize what the end result will be. So again, given a Cauchy-Euler differential equation, you're just going to really write a product of decreasing factors of m, so m minus 1, all the way down to 1 less than that order. And then plus 6 times m minus 1, all the way down to 1 less than that order, m minus 2, and so on and so forth. So that's kind of a quick way to see it, but still, there's no way, well, I don't want to say no way, but there's really the best way to do this next part is just the slow multiplication process. So doing this, I'll get m to the fourth. Let's see, as far as m cubes go, I have minus 5 of them and minus another, so minus 6 m cubes there. As far as m squareds, I have a plus 6 of them. and minus plus another 5, so that's plus 11 of those m squareds. Just double checking my math here. As far as m's go, I have a minus 6 of them, and I don't actually have any other ones there, so minus 6m. And as far as constants, I don't have any. So there we go with that. I should always check my work, so minus 5. I don't think that there's any other bit that I have there. Yeah, I don't think so. And you do the same trick for the next one in line. So I'll write this as plus. As far as m cubes, I have a positive 6 of them. As far as m squareds, I have a minus 2 minus another 1, so minus 3 times 6 is a minus 18 of those m squareds. Again, there's plenty of room for mistakes here, so watch what you're doing when you do this. And finally, as far as m's from that, I have a positive 2 times 6, or a positive 12 of them. And then we're going to combine some terms here, plus 9m squared, and then minus 6m plus 1 is equal to 0. Combine like terms, m to the fourth. Let's see, cubics. We have negative 6 plus 6. Oh, that's kind of nice. That disappears. So these are gone. As far as quadratic terms or squared terms, I have 11 of them, minus 18, so I'm at a negative 7 of them. And then I add back 9, so I have a positive 2 of those m squared terms. I don't know what just happened to that. And then let's see, it looks like minus, I must have missed a negative somewhere because as I'm seeing this, it seems to me, no, it looks like that's about right. I just wasn't seeing that 12 right there. So it's 12 minus 6 are gone. And then finally I have this plus 1 is equal to 0. Bit of a mess to clean up, but here we are. Okay, so now this will be oh no, it does factor, right? So this is m squared plus 1 squared. Great. And if you look, that's actually repeated root. The root we're looking at is imaginary, right? So if m squared is equal to a negative 1, that means m is equal to plus or minus I, and this is of multiplicity 2 because we have that power on there of 2. So let's go ahead and write out the alpha beta version of m here. So alpha is going to be 0 because there's no real part, and beta is going to be 1i. So now we know from our previous work from the theory section that if this was a single root, okay, so if it wasn't a second power here, but if it was a single root, our y sub c would be c1, actually, I'm sorry, it would be normally e to the alpha, I'm doing e to the alpha, x to the alpha, times the quantity c1 cosine of beta natural log of x plus c2 sine of beta natural log of x. That's if there wasn't a repeated root. And that's still okay, actually. But with the repetition of the root, we'll say plus, and we'll multiply that by not x, because we're working with Cauchy-Euler's, we're going to multiply by the natural log of x times x to the alpha times the quantity, and then these are different constants here, c3 cos of beta natural log of x plus c4 sine of beta natural log of x, and quantities. So now we just have to insert the alphas and the betas, and again, alpha is 0, so those x to the alphas are gone, but betas are 1. So this is going to be c1 cos of natural log of x plus c2 sine of natural log of x plus the natural log of x times the quantity c3 cosine of natural log of x plus c4 sine of a natural log of x. A bit of, obviously handiwork here. But there's the repeated root. You can actually see, right? They're the same exact terms, cosine of natural log x, and here again is cosine natural log of x. It's just the repeated term gets the natural log of x in front of it. All right, so that takes care of actually a more difficult problem, which is the repeated complex root, where the discriminant is negative. But again, notice I didn't really use the word discriminant in this entire example because I don't really look at that. Instead, I just go through and set up the characteristic equation and solve it out. If it happens to present complex solutions with imaginary parts, I'll go ahead and use this cosine sine form.